Hey there, we're going to go ahead and get started on 4.4. So let me share my screen. And slide this from the very beginning. All right, so today we're going to be talking about 4.4, real zeros of polynomial functions. And so there's quite a bit of objectives here. And so we're just going to take them one by one and just kind of slow it down, okay? So factored form basically means when your entire polynomial is written where you can see all of its factors. So the factor theorem states that a polynomial has a factor, x minus k, if and only if, when you plug in k into that function, you get out a zero. So basically, going back to our understanding of x-intercepts and the like, anytime it crosses this axis, these are called x-intercepts, roots, solutions, zeros. I'm gonna highlight on the word zeros, and that is because they are where y equals 0. They're the x places where y equals 0, okay? And so those are also called the factors, can be written, as the factors of a polynomial. And so basically, if let's say we had a parabola and that parabola crossed at 1 and 3, then the way you would write the factors is that you would say x minus 1 times x minus 3. Now it's minus because you would set these equal to 0 to solve for x. And by adding 1, you'd see that x does equal 1. X minus 3 set equal to 0. When you add 3 to the other side, you see that x does equal 3. So that's where that comes from. That's where that comes from. But these are called the factors. And that's basically what this theorem says. The best way to do these problems is, the best way to learn these problems rather, is to really just do them. So we're going to jump right in and then we'll make sense of it as we go. So use the given zeros to write the complete factored form of f of x. So f of x is given to us as this large quadratic with some coefficients for a, b, and c. And we want to be able to factor that. Remember, if we use the quadratic formula, we would get out that x equals 1/2 and x equals 4. But that's not what it's asking us to find. They actually gave us that. So we don't have to use the quadratic formula here. Instead, what we're going to be using is this theorem that tells us how to write it in factored form. Okay. So to do that, we got to ask ourselves a couple questions. The first one is, ignore that. The first question we're going to ask ourselves is, what is the leading coefficient? So in other words, what is the a value? That's 7. Okay, so we have to have that to write the complete factor form. And if 1/2 is a 0, then when you plug in 1/2 into the function, you get out 0. So by this theorem that we started earlier, we know that one of the polynomial factors can be written as x minus 1/2, because 1/2 is one of the zeros. So x minus 1/2 is one of the factors. 7 is the coefficient. Okay. Then it tells us that 4 is another 0, which means that when you plug in 4, you get 0, which means that we can write it as a factor x minus 4. So that's another one of the factors. So when we put all of this together, we have that f of x equals 7, which is our coefficient, times x minus 1/2 times x minus 4. And that is equivalent to 7x squared minus 63 over 2x plus 14. They equal each other, but it's just another way to write it. This is called factored form. Oh God. Let me see if I can write this not writing in cursive. Factored form. That is what that's called. Okay. So let's double check and make sure that we got it right. You don't have to check every one of them, but by checking that, then you know for sure you got it right. So basically we have our function of x equals 7 times x minus 1/2 times x minus 4. And we can FOIL it or we can use the box method. So in here, in this case, we're going to use the box method. So x times x is going to be giving us x squared. X times negative 1/2 gives us negative 1/2 x. Uh-oh, my pen stopped working. Okay, so we have this x times the 1/2, which should give us, let's do x times x times -4, which gives us negative 4x. Then we're going to do the x times negative 1/2, which is negative 1/2 x. And then -4 times negative 1/2 gives us a positive 2. They wrote it as 4/2 just so you can see the multiplication of fractions, but it really is a positive 2. Now we can write that in place of these factors multiplied by each other. And when we combine like terms, -4 and 1/2 is -4.5 or -4.5, which can be rewritten as an improper fraction of 9/2. And 4/2 can be rewritten as just 2. Okay, so that's how we get that inner part, which is basically the multiplication, double distribution of these two binomials. Then we take that 7 and distribute it all the way through, and that's how we end up with our original function, which is 7x squared minus 63 over 2x plus 14. These match, so yeah, we factored it correctly. So let's do another example. Let g of x be a cubic polynomial. That means it's going to have 3 factors with the leading coefficient of 5. Suppose that our zeros are -2, 1, and 2. Write the complete factor form of g of x. So the leading coefficient is 5. It told us that in the problem. Okay, so I got that from here. Then it says if g of -2 equals 0, then that means -2 is a 0. So that means one of our factors is going to be x plus 2. Okay. And the way you check that is like, basically it's the opposite thing again, but plus 2, you set that equal to 0, then you're going to end up with x equaling -2. So if you want to think about it backwards, they're telling us that -2 is one of our zeros. So x is equal to -2. So therefore, if you add 2 to the other side, you end up with x plus 2 equaling 0. And that is going to be our factor. So if that helps, then definitely do that. We also know that g of 1 equals 0. So x is going to equal 1 in one of these cases. Subtract 1 from the other side, x minus 1 equals 0. So that's another of our factors. And finally, we have g of 2 equals 0. So that means our other factor is x minus 2. So these are our factors based on this information. Being able to write that is going to be really important in terms of you seeing where these pieces come from. Now I'm going to write complete factor form. We have our coefficient times our 3 factors. And that's g of x. That's it. That's all, baby. Okay. E of 3. Example 3 says, now we're going to do this again. They're going to give us again this long polynomial that's all written out in not factor form. And we want to find the complete factor form. So the first question again is what is our leading coefficient? So we see our leading coefficient as -1/2. But then we don't know our zeros because they weren't explicitly given to us. But they were kind of given to us because they gave us this graph. From the graph, we're able to see our zeros, and they're going to be -1, 1, and 2. So to write that in factored form, this would be x plus 1, x minus 1, and x minus 2. So we got our leading coefficient, -1/2. Identifying those zeros from the graph, we see them, and we can write them in factored form, x plus 1, x minus 1, and x minus 2. Putting these 3 parts and the leading coefficient together, we have our factor form. Right now, I'm wondering like what could be difficult, what could be presenting a problem for you right now? And I think it's probably going from oh, I know my zeros. How do I write them as factors? So basically, if I were to make it in one sentence, whatever your zeros are, take the opposite and add an x in front. So if it's -1, it's going to be x plus 1. If it's it's +1, it's going to be x minus 1. If it's +2, it's x minus 2. And those are your factors, baby. So of course we want to check our work. So if you have 3 factors, then you have to multiply them 2 at a time. And so using these first 2, we're going to use the box method. X and x make x squared, x and -1, -1x, x and +1, +1x. And then 1 and -1 make -1. So when you combine those together, these guys kind of cancel each other out. And you're left with just x squared minus 1 as your first term. So then you would multiply that term with the second one. You get x cubed, -2x squared, -1x, and +2. Writing all of that out together, we have x cubed minus 2x squared minus x plus 2, all times the leading coefficient of -1. And when you distribute that -1/2, when you distribute that -1/2 for every one of those terms, you get what we started with, -1/2 x squared plus x squared plus 1/2 x minus 1. And that's just a distribution of this guy to every one of these factors. And when those 2 match, that means you did it right. Okay, so let's do another example of this. We have our f of x, and it gives us a leading coefficient of plus or minus 1, which is kind of weird. But the integer zeros are shown in the figure. So we're going to write it in complete factor form. So the first thing it says, what is our leading coefficient? Well, that was given to us. So in this case, it's either -1 or +1. And because these arrows are going down, you know that this is a negative graph. So the coefficient had to be negative. So that's why we chose -1 instead of +1. Had it been up like a cup, it'd have been positive. But because it's down like a frown, it's negative. Okay. All right, so what is the leading coefficient? We have -1. Identify the zeros from the graph. Looks like, we have -3, -2, 1, and 4. So our zeros are -3, -2, 1, and 4. So our factors are going to be x plus 3, x plus 2, x minus 1, and x minus 4. All times our leading coefficient of -1. And that's that. So let's repeat this problem. Actually, it's a video. You can stop, pause, and rewind it. All right, let's keep going. Uh-oh, what did I do? Oh yeah, when you have -1, you don't actually have to write the 1. You can just leave it as negative. Okay. Let's do it again. So we have this polynomial f of x with integer zeros. And it says, note that the leading coefficient is not plus or minus 1. Ooh. All right, let's figure this out. So we have our zeros at -1, -2, 3, and 4. So what is the leading coefficient? We don't know. Let's identify the zeros from the graph. The zeros are -2, -1, 3, and 4. We can write those as x plus 2, x plus 1, x minus 3, and x minus 4. Going from here to here is the strategy that you all have to master. If you have questions about that, we'll discuss it in class for sure. All right. This a value is we still don't know our leading coefficient. So we're going to substitute our value in for x and y, so then we can solve for a, just like we did when we had the vertex form. Okay, we could take any point on our function and solve for a. So we're going to take an easy point. And that happens to be 0.8. So we're gonna take the point 0.8. And what that means is our X is 0 and our Y is 8. So let's substitute those values in. So we're gonna put 8 in for f of X, 0 in for all of these X's, and we're gonna solve this problem, solving for A. So we have A times 2 because 0 plus 2 is 2, 0 plus 1 is 1, 0 minus 3 is -3, and 0 minus 4 is -4. So 2 times 1 times -3 times -4, I think that's positive 24. So we get 24A. So we have to divide 8 by 24 to solve for A, and that's just 1/3. So our leading coefficient is 1/3. Woohoo! Now, when you're doing this by yourself, the strategy is always to choose an easy value for your XY coordinate point. Anything with a 0 in it, anything with a 1 in it will probably present an easier situation than dealing with negatives and all of that. So definitely be strategic when you pick your points. And then you put it all together, leading coefficient and the 4 factors. Okay. So find. If the graph touches the x-axis but doesn't cross it, then we say that that has an even multiplicity. Okay. If the graph crosses the x-axis, then we say that 0 has an odd multiplicity. So like when it just bounces off, like right here. Yeah, we say that 3 is a 0, but it has multiplicity. Okay. We'll talk about what that exactly means in just a second. So if the graph levels off more, then it has an even higher multiplicity. So example 6 says the graph of the polynomial f of x is shown in the figure. Estimate the integer zeros and state whether or not the multiplicities are even or odd. So because it actually crosses right here at 2, we're going to say that that's an odd multiplicity because it actually crosses the graph. Versus at number x equals 3, it comes, touches 3, and bounces back off. So that means it's even multiplicity. So if it just touches it but doesn't cross, then it has even multiplicity. So -2 has an odd, and +3 has even multiplicity. Again, we're going to define this word in just a second, but I need y'all to understand how to find out if it has even or odd multiplicity. Okay. So a polynomial with degree 5, a 5-degree polynomial, that means that it has 5 factors. Okay. A 0, 1 with multiplicity 2, and a 0 of -3 with multiplicity 3 is written as f of x equals x minus 1, because we have a 0 at 1, squared, because the multiplicity is 2, so it means twice, and then a 0 at -3, hence the x plus 3, with multiplicity 3, cubed, because of multiplicity 3. So it just tells you how many of those factors there are. That's what the definition of multiplicity is. So example 7, write the complete factor form of a polynomial that satisfies these conditions. Let the leading coefficient be 1. So it's a 4th degree polynomial. So we're gonna have 4 factors or 4 zeros. And we're gonna write it in complete factor form. So we have a 0 at -1. That means x plus 1 is our factors. Multiplicity 3 means that it's cubed. And 2, so x minus 2 is one of the factors with a multiplicity of 1. Remember, when it's a multiplicity of 1, we actually don't have to write that. That's it. Okay, that's it. That's all. So that is our factored form. X plus 1 to the cubed power, or to the 3rd power rather, and x minus 2, single, because there's just one of them because the multiplicity is 1. Okay. All right, let's do example number 8. The graph is either cubic or quartic or quintic. Lord, they gave us 3 options. When it says cubic, quartic, or quintic, that means that it could have 3 factors. 4 factors, or 5 factors. And the zeros are shown. Uh-oh. I went too fast. There we go. So cubic means 3 factors, quartic means 4 factors, and quintic means 5 factors. It says write the complete factor form and assume that the leading coefficient is plus or minus 1. Well, we know we're going to go with a plus 1 because our polynomial is smiling. It's up like a cup. Okay. Okay, so we know that that's going to be leading coefficient of 1. Okay. Identify the zeros from the graph. It looks like this kind of flattens out before it just crosses. So we know there's going to be some multiplicity here at 2, negative 2. So one of our factors is going to be x minus 2. And then this factor, it just crosses. It doesn't flatten out or anything. So we know our other factor is going to be x. I'm sorry, that's x plus 2, sorry. And this is x minus 1. We just need to find the multiplicity. So our factors, our zeros are at negative 2 and at 1. Okay. So the graph crosses the x-axis at these zeros. So both of the zeros are going to have odd multiplicity because they don't just bounce. Remember, if they bounce, it's even. So because they're odd, because they cross, it's going to be an odd number. Now, we know that the multiplicity at x minus 1 is just 1. Uh-oh. Sorry, I don't know what's happening. So anyways, so x, I want to just explain this before I show you what the answer is. This one is going to have a multiplicity of 1. This one, on the other hand, needs to have odd multiplicity. It can't have 1 because it doesn't just cross. It like flattens out. It can't have 2 because it has to be an odd number. So we need to have a 3 as a multiplicity because it has to be an odd number because it crosses, and it doesn't just cross straight like it does here because it flattens out. So that means that this would need to be quartic. This would have to be a quartic function because 1 plus 3 is equal to 4, and 4 is when we get the quartic function. So, for example, if 1 had a multiplicity of 1 and then negative 2 had a multiplicity of 3, this would make it a 4th degree polynomial or a quartic function. Okay. This is the only possibility that satisfies the directions of it being cubic, quartic, or quintic. Because if it was cubic, then this would have to be 2. And we know we can't have a 2 because it's even. If it was quintic, it would have to be a 4. And of course, we can't have 4 because that's even as well. So therefore, the only option was 3. So therefore, 1 plus 3 is 4 into quartic. So you write it like this. It doesn't matter which one goes first. It don't matter. All right, so again, we have this situation. It's cubic, quartic, or quintic. So we got to use a little process of elimination. This time it looks like they're touching, but they're not crossing. So that means it's going to be an even number. And this is going to be an even number for multiplicity. Where did they cross at? It's crossing, where did they touch at? negative 1 and positive 3. So our factors are going to be x plus 1 and x minus 3. Okay. And we actually don't know the multiplicity, but we know that they both have to be even. So if you have 2 numbers that are even, there's no way you can get a 3. There's no way you can get a 5. So it's not cubic or quintic. In this case, it had to be quartic again. And this would have to be 2 and a 2. You can't get 3 by adding 2 even numbers together. You can't get 5 by adding 2 even numbers together. So therefore, it left us with the only option of having a 4, which was quartic. Okay. What is the complete factor form? Because we don't know the coefficient. So what we'd have to do here is probably solve for A. So leading coefficient, we don't know. Identifying the zeros, we got negative 1 and 3. Since they just touch, they both have even multiplicity. So this has to be a fourth degree polynomial or quartic function. All right, so we have basically a times x plus 1 squared and x minus 3 squared. So we have to solve for a because we don't know the leading coefficient. Now, because we don't know the leading coefficient, we're going to take a value off this chart. You could use any value you want. Okay. The textbook is choosing 2, -6. Again, you don't have to use this point. You can use any point that makes sense to you. I will use 0, -6. Okay. You plug those values in. You plug in 2 for x and -6 for y. A is 3 squared. I mean, a times 3 squared and 1 squared. So you get, in this case, or -1 squared, and you still get 1 and 9. 1 times 9 is 9. So you get 9a. Divide by 9 to solve for a, and you get -6 over 9, which is also -2/3. A equals -2/3. So there we have it. We substitute that a value in, -2/3, times x plus 1 squared times x minus 3 squared. Satisfies all the conditions that were given to us. Ask questions if you don't understand this in class when we go over this. Example 10. We now are given the function and we're asked to find the x and the y intercepts. So the x-intercepts are pretty easy to find because those are the factors. So in this case, we have x plus 1 being the factored form and just x. Oh, wait, we're going to start with finding the y-intercept, sorry. So we let x equal 0 because anytime you have a y-intercept, the x value has to be 0. So we go into our function and just plug in 0 for everywhere the x is, and we can solve and find our y value. So in this case, our y value is 0 as well. So the x-intercept is 0, 0. For the x-intercepts, we let the y be 0. So you set it equal to 0. And because of the factors, you know the zeros from looking at the inside of the problem. The zeros are -1 and 0. So it was x and x plus 1. You're basically going to take that x and set it equal to 0, and then take the x plus 1 and set it equal to 0. So x plus 1, you subtract 1 on both sides, you get x equals -1, x equals 0. So these are your x-intercepts. Alternatively, you could do what this is doing right now and solve it algebraically. Okay, determine the multiplicity for each 0 of f. So we have the function again. The multiplicity here is 1 because you didn't write it, and here it was 2. So we have the odd multiplicity of 0 being 1. Because remember, if you have x minus 0, you don't have to put the 0 in there. Even if you had x plus 0, you don't have to put the 0 in there. That's why you just see x as one of the factors. Okay. So we're looking at this as a factor, and it has multiplicity of 1, which is odd. That means that at 0, it crosses. And x plus 2 squared means that we have a multiplicity of 2, which means it just touches, but it doesn't actually cross. What do we know about the graph? Let's look at it. The graph, we know it's upside down because the coefficient is negative. So we know the arrows are going to be going downwards. And we know that it's cubic because we have 1 plus 2 makes 3. So it's a cubic function. We know that it crosses at 0 and it just barely touches the graph in -1. So the basic shape of the graph is this. So you got -1 and 0 where things are happening. It's going to just touch at -1. And remember, it's going down. That bottom arrow has to go down because it's a negative graph because of that coefficient. So that's that. Okay. Sketch the graph by hand. So we know the shape, but we don't know the points. So to help us with this, we'd actually put in points and help us kind of figure out the graph. So -1 and 0, we know that those are zeros, so we can start there. Then let's plug in -3 to our function. So if you plug in -3, you get a 12 out. And that's by putting -3 in for x. So -3 times -4 squared. -4 squared is 16. Uh-oh, what am I doing wrong? That's supposed to be a +1, sorry. So it's -2. -2 squared is 4. 4 times -3 makes -12, but times a whole negative, we get +12. And that's where we get that from. We plug in a half, because we're looking for something in between here. So -1/2. That's 0.125 if you substitute that in. I would actually just use a calculator for this. Plugging in 2, you get -18. So you kind of get the shape of our graph. If you substitute this in the calculator, then you don't have to do those things by hand like I was just doing up there in the right-hand corner. All right, so it says find all the real solutions, solve the equation. So what we're gonna do here is we have these values, we can factor, okay? So we basically have x² minus x³. And so we're gonna find the factors of this. So basically, they're using the box method to separate them and kind of figure out what did I do to get those answers in the box. And so x² times 1 makes x². x² times -x makes us the -x³. And that's how we get those factors and we can solve. Another way I would do it before we go to the next one is I would say, what do these guys have in common? They both have at least 2 x's. So I take out 2 x's. If I take out 2 x's, I'm left with 1 because x² times 1 makes x². And if I take the 2 x's out here, I'm left with a -x. And that's because x² times -x makes -x³. Okay. And that is where these factors come from. Then you set each one of these equal to 0, this one and this one. So x² has to equal 0, which means x equals 0, because when you take the square root of 0, you get 0. And then we can solve for x here by adding x to the other side. X also has to equal 1. So here are our answers. These are our 2 solutions. Now for B, these numbers don't have something in common. You say, oh, 3, a 3 goes in there, but a 3 doesn't go here. So we can't do anything with that. So we'd have to solve this in a different way. They don't all have an x. They don't all have anything in common. So in order to factor this, we're going to have to look at it differently. And the box method is where they're going to fill in all 4 of those terms. The 9x³, the 27x², the -2x, the -6. And they say, hey, what and what could potentially give me 9x³? Well, what about 9x² and just an x? That would work. And this is trial and error, y'all. How did they come up with that? The reason why they came up with that in reality is they looked here and here and they said, what do they both have in common? These both have a 9 because you can pull a 9 out of both of these. That's where that 9 comes from. They both have 2 x's in common. So that's how they pull that out. Then they say, oh, well, what's left if you pull out a x², just an x? The question here is if you pull out a 9, you're left with a 3. Okay, so that's how you get the +3. Then when I look down here, 9x³ minus 2x The only thing they have in common is x. So when I pull out an x from here, I'm left with -2. Okay. And when I pull out a 3 here, I'm left with -2. So these are my factors. So I will write them like that. So then you set each one of those equal to 0 and you solve. So x plus 3 equals 0. That means x equals -3. And 9x squared minus 2 equals 0. You're going to add 2 to both sides, divide by 9, take the square root. And that's how you get plus or minus the square root of 2 over 9 as another factor. So that is solving. And basically, that's how you do it. We'll do more practice problems it is in class, but I definitely wanted you to be able to see that application of solving polynomial equations. All right, y'all. Oh, sorry, you can keep going. Square root of 9 is actually a number. So if you split the square roots, then the square root of 9 becomes 3. You don't really want to square root in the radical. It's what we call tacky in math, okay? So you don't want to leave it like this. You separate it and you solve. So the 3 solutions are -3, square root of 2 over 3, and negative square root of 3 over 2 over 3. You knew that there were 3 solutions because the degree is 3. Here you knew that there were supposed to be 3 solutions as well because the degree is 3, but x equals 0 is counted twice because it has double multiplicity. All right, that's all. That was a very long one, so take your time with this one and we'll talk a lot about this in class.